Hello viewers, welcome to this series of lectures on stereochemistry of organic compounds. Stereochemistry involves the study of arrangement of atoms of a molecule in three dimensions. This word stereo is basically a Greek word which means solid, and this solid is used to signify the three dimensions or the space, and in the same sense it is used in chemistry. So we also call it as a spatial arrangement of atoms in a molecule. The second aspect of stereochemistry is the spatial changes that may occur during a reaction. But one of the most important aspect of stereochemistry is isomerism, and our today's session is basically on isomerism. We have outlined today's session as what is isomerism, then we'll take up types of isomerism, constitutional isomerism and its types mainly will be discussed today, because the other type of isomerism, that is stereoisomerism, we shall take up in a later session. Then we will take up some misconceptions that do occur during isomerism, and finally we'll summarize the today's session. Now, what is isomerism? Isomerism itself consists of two Greek words which are called isos and meros. Isos means equal, meros means parts, means something which is made up of equal parts. Here it is considered in terms of organic molecules as molecules which are made up of identical number of atoms. In other words, we will say the molecules which have the same molecular formula. So isomerism is defined as existence of two or more compounds with the same molecular formula but different properties. Because if they show the same properties and same molecular formula, it means it is the same compound. So they become different due to some sort of difference in the arrangement. Such compounds are called isomers. Means these are the compounds which show some difference in their properties. These properties may be physical or chemical or both. So we define isomerism as the phenomena by virtue of which compounds with the same molecular formula show some difference in their properties, may be physical or chemical or both. Isomerism may be further classified into two main types. These are constitutional or structural and stereoisomerism. Constitutional isomerism means when the compounds differ in their bond connectivity, that is, atoms are attached to each other in different ways. Whereas stereoisomerism includes in which the attachment of the atoms to each other remains the same, but they differ in their arrangement in three dimensions. Stereoisomerism can further be divided into two types. These are configurational and conformational. We will discuss about this in our future sessions. Today we will concentrate on constitutional isomerism. This term constitutional isomerism is also known as structural isomerism, but according to recent IUPAC rules, it has been decided that constitutional isomerism be the terms should be used. So structural isomerism term, which was used earlier, has been abandoned now. Constitutional isomerism refers to existence of different compounds having the same molecular formula but different sequence in which the atoms are bonded, that is, in their connectivity. Constitutional isomerism is of 6 types. Out of these, 3 are the main types. These are chain isomerism, position isomerism and functional isomerism. And then 3 are special cases: Metamerism, which is the special case of position isomerism; Tautomerism, which is the special case of functional isomerism; and ring chain isomerism, that is the special case of chain isomerism. Now we shall take up these one by one in detail with the help of some examples. Chain isomerism: existence of 2 or more compounds having similar molecular formula but different carbon skeleton. They are called chain isomers. Now, as you know that carbon is attached to other carbon, they may form chains. 2 carbons, they will form ethane, 3 carbons, they will form propane, and when we reach to 4 carbons, we get butane. But in 4 carbon compounds, it is not always necessary that 4 carbons are attached in a straight chain as shown here. There can be two different arrangements for this. One is that carbons are attached to each other forming a chain like this. We call this compound as butane. But there is other possibility that there is a chain of 3 carbons, 1, 2, 3, and this carbon as a methyl group is attached to carbon number 2 of this chain. This compound is called 2-methyl propane. Now these two are different compounds, although both of them have the molecular formula C4H10, but their properties will be different, their structure is different. So that is why they are classified as constitutional isomers or structural isomers, and then specific of case chain isomers. Another example of chain isomerism we can take in a 5 carbon chain, that is pentane. Now these 5 carbons, they might be attached in a straight chain, or there may be a chain of 4 carbon and 1 carbon group is attached as a side chain, 2-methyl butane. Or another example, there may be a 3 carbon chain and 2 carbons are attached as side chain as 2-methyl groups. So this is 2-methyl butane, or this is 2,2-dimethyl propane. Now all these 3 are the compounds which are isomers of each other, differing in the arrangement of atoms in their skeleton. So they are classified as chain isomers. Next type of isomerism is position isomerism. Position isomerism is when the functional group or any of the substituent is present at different positions on the same carbon chain. Means carbon chain should be same, the skeleton of the carbon should be same, but the substituent or the functional group, they may be present at different positions. For example, we have this compound which is called 1-propanol. This is an alcohol of 3 carbon, and this hydroxyl group is attached at carbon number 1 of this chain. Now another example of this 3 carbon alcohol is 2-propanol. In this case, an alcoholic group is attached to carbon number 2 of the chain. So these two compounds, now they have the same number of carbons, same number of hydrogen, 1 oxygen each. It means they have the same molecular formula. But where do they differ? They are differing in the position of hydroxyl group. In one case it is at carbon number 1, in another case it is at carbon number 2. So they are classified as position isomers. So position isomers can be when the functional group is present at the different position of the same chain, or any other substituent also that might be present at different position in the chain. There is another example. This compound is a 4 carbon molecule with 1 double bond. So this is basically butene, and since double bond is present between carbon number 1 and 2, it is called as but1-ene. Another isomer is when the double bond is present between carbon number 2 and 3. This compound is called but2-ene. So where do they differ, these two compounds? These two compounds differ in the position of this functional group, that is the double bond. In one case it is present between carbon number 1 and 2. In another case it is present between carbon number 2 and 3. So they are also classified as position isomers. Now we have functional isomers. Functional isomerism, when compounds have the same molecular formula but they have different functional group. And obviously if they have the different functional group, they will show much difference in their chemical properties also. Let's take one example. It is propanol. It is a 3 carbon compound having a carbonyl group at carbon number 1. It is aldehyde. Another can be a 3 carbon compound with a carbonyl group at carbon number 2. This is a ketone. They are named as propanol and propanone, but they show different properties because one is having hydrogen atom attached next to the carbonyl, whereas in this molecule we have 2 methyl groups attached to the carbonyl group. So in both the cases we find the carbon chain is of 3 carbons, but in one case this oxygen is attached at carbon number 1, in this case oxygen is attached at carbon number 2. So they have different functional groups and they are classified as functional isomers. Another example of functional isomerism we can take from alcohols. Like this is a simple molecule ethanol with having hydroxyl group at carbon number 1 in this case. Another molecule can be when there are two methyl groups attached to oxygen. Means this methyl group which was here is now on this side of the oxygen. This compound is an ether. It is named as methoxymethane. This is ethanol. Both are having different functional groups. Hence they are classified as functional isomers. We shall now take some special cases of constitutional isomerism, and one of them is metamerism. In metamerism, we find that functional group comes in between the carbon chain and it breaks the continuity of carbon chain. And when this carbon chain is broken at different position, then we call it as metamerism. Means it is a special case of position isomerism where the functional group breaks the carbon chain at different position. Let's take the examples. One compound is this ethoxyethane. This is an ether. In ether, oxygen comes in between the carbon chain and we find that there are two ethyl groups on each side of this oxygen. Then another ether with the same molecular formula is methoxypropane. Here the oxygen breaks the carbon chain and two fragments of chains we have a 3 carbon portion and 1 carbon portion. So these two cannot be classified as chain isomers because carbon skeleton is not the same, and they cannot be classified as the position isomers because requirement there is functional group or a substituent should be present at different position on the same carbon chain. Here the carbon chains are different. So that is why this becomes a special case and we call it as metamerism. These two isomers are called as metamers. So whenever functional group is such which is coming in between the carbon chain and breaking it at different positions, those isomers are called as metamers. The phenomena of metamerism can be shown by many other functional groups which break the carbon chain, such as esters. We have the example here for esters. This is ethyl ethanoate and this is methyl propanoate. This oxygen of the ester link breaks the chain. What we find here, this is a 2 carbon chain on this side and 2 carbon chain on this side. Whereas in this case what we have a 1 carbon methyl group on this side and a 3 carbon chain on this side of oxygen. So both have the same molecular formula, both are esters, but the functional group is present at such a position that the carbon chains on the two sides of oxygens are different. So these two esters are also classified as metamers. The phenomena of metamerism can be shown by acid anhydrides and secondary amines also. Next special case of isomerism is tautomerism. Tautomerism is a special case of functional isomerism, and in this case what happens, the functional groups are interchangeable and they interchange by movement of one hydrogen. Such a hydrogen which can change its position is called labile hydrogen atom. Tautomerism is further classified by naming the two functional groups which are in equilibrium with each other, that is, which are formed by the exchange of hydrogen atoms. Let's take one example. Since this compound has got a carbonyl group, it is called keto form, and after the shifting of this hydrogen, this has become OH, that is alcohol, and this has become double bond, means ene. So such compounds are called enol. So these compounds are called keto and enol, and this type of tautomerism is classified as keto enol tautomerism. Tautomerism can be shown by many other functional groups like amide groups. This is an amide, CONH2. One of the hydrogen from nitrogen can shift to this oxygen and the pi electron shift here between carbon and nitrogen to form the double bond, and this structure is known as imine, C double bond and imine, and OH all. So it is called iminol, and this is amide. So this tautomerism is called amide iminol tautomerism. Oximes can also show this type of isomerism. This is an oxime, C double bond NOH. This hydrogen from the oxygen it leaves and hydrogen comes to this carbon, double bond shifts between nitrogen and oxygen. we get this functional group which is called nitroso. So this is an oxime nitroso tautomerism. So in tautomerism, what happens? Two functional groups, they remain in equilibrium. The ratio of the two compounds will depend on many factors like solvent, temperature, overall pH, and even the stability of individual molecules. It is not necessary that in one amide, if the ratio of the amide molecule is more, in another compound also it remains the same. It may vary because overall stability of the molecule will also play a role here. How actually this movement of hydrogen occurs, we can understand from this diagram. It is this hydrogen which is shown here in red, which is moving or which is labile hydrogen. Now it is not the same hydrogen that is going to this position. Actually what happens, one of the molecule, maybe water or other solvent molecule, may capture this hydrogen. The pair of electron moves here, it forms a double bond between these two carbon atoms. These pi electrons shift to this next atom, and this atom captures the hydrogen from another solvent molecule, and we get this structure. So this was a keto structure, and here we have got an enol structure. Now keto structure, the hydrogen that was lost from here, it is not the same hydrogen that has come to the enol. This hydrogen has come from another molecule. So this is the way this movement of hydrogen occurs in this keto enol tautomerism, or maybe in amide, or maybe in oximes, in all this. Ring chain isomerism. In order to understand this type of isomerism, let's first look at the structure of these three compounds. The first compound is ethyl cyclopentane. The second is methyl cyclohexane, and this third is 1,2-dimethyl cyclopentane. All these three compounds, they contain 7 carbons. Now if we look at the continuity of carbons in them, in the first one, let me count 1, 2, 3, 4, 5, 6, 7. So what we find that 7 carbons are in a chain, and carbon number 7 is linked to carbon number 3. Let's move on to second structure. Again we find 1, 2, 3, 4, 5, 6 and 7. So there are 7 carbons in a chain, but 7th carbon is linked in the chain to carbon number 2. And in this case 1, 2, 3, 4, 5, 6, 7. But we find here that it is the 6th carbon that is linked to carbon number 2. So what difference we find in these molecules is that it is the same chain, but only the different carbon of the chains have linked to each other at different positions. So how do we classify these isomers? They have the same chain, so we cannot classify them as chain isomers. They do not have any functional group, so they cannot be classified as functional isomers. There is no questions of position since there is no functional group. We can talk about the position of substituent, but substituents are different. Here the substituent is methyl, here there are 2 methyls, and in this case it is ethyl. And second thing, the substituents are present on a different type of base, that is, it is a cyclohexane, it is a cyclopentane. So then a special case of isomerism is generated here, and we call them as a ring chain isomerism. That is when the same number of carbons are there in the chain, but they form the ring of different size, and obviously the remaining carbon chain will also be of different size. So they are classified as ring chain isomers. Then there are some misconceptions in isomerism. The problem comes sometimes in classifying the compounds into a particular type of isomer, such as these two compounds. Both of these are 5 carbon compounds, 1, 2, 3, 4 and 5. Both of them have carbonyl group. The difference is that carbonyl group in this compound is at carbon number 2, whereas in this compound it is at carbon number 3. Now what we find that both are ketones, both have the same molecular formula, both have the same functional group. Mistakenly, these two compounds are sometimes classified as metamers, which is not correct. Because metamers means functional group should be such which breaks the continuity of carbon chain. Here the carbonyl group does not break the continuity of carbon chain because one of the carbon of carbonyl group is part of the chain. So they are classified as positional isomers. So 2-pentanone and 3-pentanone are positional isomers and they are not metamers. Let's take another example. This is an ether and there is another ether with the same molecular formula. We find that there is a 3 carbon chain on one side and 1 carbon chain on another side. In this also there is a 3 carbon chain on one side and 1 carbon chain on another side. So they are not metamers because they have the breakage of the carbon chain at the same site 3 plus 1 and 3 plus 1. Then what type of isomers are these? They are not the functional isomers because they have the same functional group. Let us look at the position of this group, that is the methoxyl group. We find that this methoxyl group in this chain is present at carbon number 1, whereas in this chain of 3 carbon it is present at carbon number 2, and they are named as 2-methoxypropane and 1-methoxypropane. So they are classified as position isomers. They are not functional isomers and not even metamers. Another example we take from amines. This is ethanamine. This is N-methyl-methanamine. So both have the same molecular formula. Again, mistakenly they are classified as tautomers because this is breaking the carbon chain. Okay, this is breaking the carbon chain, but with that the functional group has also become different. This is a primary amine. This is a secondary amine. So they are different functional groups. So they are not classified as tautomers. They are basically classified as functional isomers. We can compare them with ethanol and methoxymethane. It is the same situation. This is an alcohol with OH group. And now what happens? One of the methyl group comes on this side of the oxygen. So this becomes ether. So they are two different functional groups and they are classified as functional isomers. Similarly, primary amines and secondary amines, they are classified as functional isomers. Let's take another example from the amines, propanamine. Propanamine can be propane 1 amine and propane 2 amine. The amino group is present at carbon number 1 or it is present at carbon number 2. So they are position isomers. Same molecular formula, but the position of NH2 group is different in the two. Then another compound with the same molecular formula is this, where NH group comes in between the chain, and this is N-methyl-ethanamine. Now this is a secondary amine. So this is a functional isomer for this compound as well as for this compound. So where do we actually get metamerism in amines? That we can see in these examples. This is N-methyl-propanamine, means it's a secondary amine with 1 carbon chain on one side and then 3 carbon chain on another side. And another example is 2 carbon chain on this side and 2 carbon chain on this side. So N-ethyl-ethanamine. Now these are the two compounds. Both of them are secondary amines, but they have the functional group at a position which is breaking the carbon chain at different positions. So they are actually classified as metamers. So what we find that sometimes it becomes difficult to identify the type of isomerism shown by the two compounds. I'll tell one of the simplest way of doing is that write the IUPAC name of that compound. Once we have written the correct IUPAC name of the two compounds and we compare, if they differ in the ending, means ending is the suffix part which is due to functional group, it means they are the functional isomers. If they differ in the middle part gives us the total number of carbon in the chain, it means then they are chain isomers. And if they differ somewhere in the mathematical numerals, means the position of the functional group or position of any substituents, then they are classified as positional isomers. So we can find out the type of isomerism shown by two compounds in most of the cases by comparing their IUPAC names. Let us now summarize what we have done today. We discussed what is isomerism, then we discussed the types of isomerism, out of which discussed only one type today, that is the constitutional isomerism, and then various types of constitutional isomerism. Then we have taken some misconception that arise while classifying the compounds into a particular type of isomer. In the next session, we shall take up stereoisomerism, its classification, and then one type of stereoisomerism, that is geometrical isomerism, will be discussed